Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about multiple testing. Up to now we have studied hypothesis testing under the assumption that we were interested in evaluating a single hypothesis. However, in many applications it is often of interest to test multiple hypotheses at the same time. This is dangerous because the guarantees provided by the hypothesis testing framework no longer hold in such cases. In this video, we're going to explain why that is the case and what we can do about it. Let's get to it. We're going to talk about multiple testing, but let's begin by reviewing the hypothesis testing framework. In hypothesis testing, we begin by choosing a conjecture. Then we choose a null hypothesis that contradicts that conjecture. We choose a test statistic that should be large if the original conjecture holds. A large test statistic is evidence against the null hypothesis. Then we decide on a significance level alpha, which is often set at 5%. We gather our data, we compute the test statistic, and then we compute the p-value corresponding to the test statistic. The p-value is going to be small if the test statistic is large. We then check whether the p-value is smaller or equal to the significance level. If that is the case, we reject the null hypothesis, which is interpreted as evidence in favor of the original conjecture. If we do all of this, we're guaranteed that the probability of a false positive, the probability that we reject the null hypothesis when it holds, is bounded by alpha, by 5%, if that's what we have set the significance level to be. The whole framework is set up to protect ourselves from false positives. Alright, so in order to motivate multiple testing, let's start with an example. We're going to evaluate whether NBA players are clutch. And a player is called clutch by fans and sports journalists if they play better when it matters. We're going to evaluate whether that's the case for players in the NBA in the 2014-2015 season, and we're going to focus on three-point shooting. Clutch time, the time when it matters, is going to be defined as the last quarter of games that are relatively close. So it's the fourth quarter of games that are decided by 10 points or less. Our conjecture is that the player gets very motivated and focused and plays better during this clutch time than the rest of the time. The null hypothesis is that that is not the case. The player shoots exactly the same in the clutch as the rest of the time. Our test statistic is going to be the number of threes made by the player during clutch time out of the total number of threes that they attempt. If the player makes a lot of threes, if the clutch three-point percentage of the player is very high, then this is evidence in favor of our original conjecture and against the null hypothesis. All right, so let's set up a hypothesis test. Our hypothesis test is going to be very similar to the one that we designed for the biased die example. So you can check out that video for more details. But basically, we're going to say that under the null hypothesis, the probability of making each clutch three is the same and is equal to the season percentage of the player. The distribution of the test statistic under this null hypothesis, if we assume that the free throws are all independent, is going to be a binomial with parameters n, where n is the number of threes attempted in the clutch, and the theta parameter is going to be equal to the season percentage of the player. Now we want to compute the p-value corresponding to the number of threes made by the player in the clutch. This is the test statistic t data. Well, we need the probability that the test statistic under the null hypothesis is greater or equal to t data. We know it's PMF. It's binomial with these parameters. So we just need to sum the PMF from t data to its maximum value, to the maximum value of the test statistic, which is the number of threes. Okay, so we're summing from t data to n. What are we summing? The PMF of the binomial. This gives us the p-value for each player. When we look at the p-values, if we set the significance level to be 0.05, we see that there's 5 players for which the p-value is below that threshold. The most convincing is Covington. I hope I'm pronouncing his name more or less okay. His season percentage is 38%, but his clutch percentage is 73%. Very impressive. The p-value is very low. Okay, and similar results for these other players. I'm happy to see Mirotic here. He used to play for the Spanish national team, even though he's from Montenegro. Okay, so now let me ask you, are you convinced? If we were sports journalists, we would go ahead and write an article about how these players are really clutch. This was during the first half of the season, so we would go and write, this season these players have demonstrated that they're clutch, and then tell some personal stories about them or something. But we're data scientists, okay? So as a data scientist, it's always a good idea to test your conclusions on some new data, if you can, some held out data. That's always a good idea. So I actually saved the second half of the season to test our conclusions. So when we look at the second half of the season, what we see is that we don't get the same results. Like definitely the p-values are all way above the threshold, but even more worryingly, for a couple of the players, their clutch percentage is actually lower than their season percentage. And this happens in particular for Covington, who was the player for which we were the most convinced. So what is going on? What is going on? Maybe pause the video and think a little bit about what do you think is going on. So what's going on is that the probability of a single player overperforms by chance is actually very low. This is what the hypothesis testing framework guarantees. But we're actually testing 146 players. The probability that a few of them overperform by chance is much higher. To show why, let's remember that we had derived the p-value distribution under the null hypothesis when we were talking about statistical significance. For continuous test statistics, the distribution of the p-value under simple null hypothesis is actually uniform. Okay, and this also holds approximately when the statistic is discrete, and we could generalize this to obtain a bound for composite null hypothesis. But just to simplify the exposition, let's think about a continuous simple null hypothesis. In that case, if we look at many p-values obtained from test statistics that are sampled from the null hypothesis, so nothing interesting is happening, basically the p-values are going to be uniformly distributed between 0 and 1. This is very good news if we're just doing a single test. Why? Because what is the probability of a single false positive? Well, it's the probability that the p-value by chance ends up being very small, right? What is that probability? I have actually occluded the alpha. The probability is exactly the significance level alpha, which is often 5%. Okay, again, this is exactly the reason why we set up the hypothesis testing framework in order to protect ourselves from false positives, in order to ensure that the probability that the p-value is small is bounded by the significance level. Great. But now, in our example, we're actually applying many hypothesis tests, 146. There were 146 players in our data set. So what happens if we do many tests? How many of them are going to be false positives? For how many of them, just randomly, the p-value is going to end up here? Well, for a fraction equal to alpha, 5% of them if alpha is equal to 5%. And that's exactly what is happening for our clutch example. So here are the p-values for all the players. This is roughly uniform. So just by chance, we get 5 players that end up there, by mere chance. But if I only tell you about those 5 players, it might sound as if they're shooting much better in the clutch, but I've selected them among all of the players that had p-values distributed between 0 and 1. Hopefully that makes sense. And this is the problem of multiple testing. Imagine that you perform k independent hypothesis tests with significance level alpha. What is the probability that we observe a false positive? So we're going to, like the null hypothesis holds for all the tests. There's nothing interesting to see, but what's the probability that by chance one of the p-values is very small? Well, the probability of seeing one or more false positives is 1 minus the probability of seeing no false positives. If the probability of a false positive in each test is alpha, which we can achieve because this is the guarantee that is provided by the hypothesis testing framework, as we explained in the video on statistical significance. Then if the probability of a false positive in each test is alpha, this guy is 1 minus alpha, right? So we get 1 minus alpha to the k because we have k tests and they're independent. So we can just multiply the probabilities that there's no false positive in the first one, no false positive in the second one, up to the kth one. Okay, great. So what is this probability, for example, when alpha is equal to 5% and we have k equals to 100, which is close to what we had in the clutch example? Well, 99%. So 99% of the time, we're going to see at least one false positive. So if we do this procedure that we did with the clutch example, where we just applied many hypothesis tests and chose the ones that were statistically significant, then very likely we're going to end up with false positives, even if the null hypothesis holds for all the tests. And of course, this is highly problematic. So what can we do? Well, depending on the value of k, if we have a p-value that is extremely small, then that still might be evidence against the null hypothesis. So let's see. We want to find a p-value threshold that is stricter so that we keep the probability of a false positive below alpha when we are doing k tests at the same time. How can we do that? Well, the probability of a false positive is the probability of the union of having a false positive in each of the tests. Now we would like to bound the probability of this union, and for that we're going to introduce a very commonly used result in probability theory, which is the union bound. The union bound tells us that the probability of the union of k events is bounded by the sum of their probabilities. This is quite easy to prove. I'm going to kind of show you a proof based on Venn diagrams. So imagine that we have, I'm going to do it for like 3 events, okay? You don't remember this, like you can go back to the videos on probability spaces and you will see that we could represent events using Venn diagrams, and that makes, the proofs quite intuitive. For these Venn diagrams, the probability is represented by, let me choose another color. The probability of this event is the area of the event, okay? So that area that I have just colored is probability of A1. Now you can see that this guy is probability of A2, and this guy is probability of A3. What is the probability of the union? The probability of the union is the probability, let me put it in yellow, the probability of this region. It's obvious that the probability of the whole region is smaller than the sum of the individual probabilities, because we can decompose the region in different, I feel like I might be making this more complicated than it is, in 3 kind of slices, like in this slice, and this slice, that are all smaller than the original event. Okay, so hopefully this visual proof convinces you. The probability of a union of events is always bounded by the sum of the individual probabilities, and that's a union bound. So then let's go back to our problem where we're saying, okay, I want a bound on the probability of a false positive. That's equal to the probability of the union of having the events having a false positive in each of the tests. This is bounded by the sum of the probabilities of having a false positive in each of the tests. Now, the hypothesis testing framework ensures that this is going to be below the significance level of each of the tests. Okay? But what we want is to be even stricter. So here we're going to have k times the significance level, or the threshold that we have, rather the p-value threshold for each of the tests. We know that if we threshold the p-value by tau, the probability of that there's a false positive in the individual test is bounded by tau. We proved this in the video on statistical significance, but now we have this factor this factor k in front. So how do we ensure that k tau is smaller or equal to alpha? Well, we need tau, the threshold on the p-value, to be alpha over k. That's called Bonferroni's correction or Bonferroni's threshold. If we apply this stricter threshold, then we will be guaranteed that the probability of a false positive is bounded by alpha. Let's apply this. Okay, that's the guarantee that is provided by Bonferroni's correction. Let's apply this to our example. Remember that we had seen these p-values. We cannot threshold them using 5% if we want the probability of a false positive to be bounded by 5%, because we're doing multiple testing. We're testing 146 players. Instead, we have to do 5% divided by 146, which happens to be 3.42 times 10 to the minus 4, and this is the actual threshold that we should apply. And when we use this threshold, we see that none of the players are under the threshold. So in this case, Bonferroni's correction tells us that we don't have enough evidence to declare that any players are clutch, which actually kind of corresponds to what we observe when we check what happens in the second half of the season. So here, Bonferroni's correction saves us from incurring in false positives. Now let's take a look at a second example where we're also going to evaluate NBA players. Now we want to evaluate the impact of a player on team performance in general. How are we going to do that? Well, we're going to check the mean point differential of the team when they have the player and when they don't have the player. Okay, just the mean point differential is by how much they win or lose on average with and without the player. Our test statistic is the mean point differential with the player minus the mean point differential without the player. If a player is very good, then presumably when they're playing with him, they will win by more, and when they play without him, they will suffer, okay, and they will win by less or they will lose by more, okay? That's the logic. So now we apply this to NBA games between 2012 and 2018. And these are the players that have the highest mean point differential. In case you don't follow basketball, I will tell you that if you did follow basketball, you would be surprised by this, because you would definitely identify this gentleman, LeBron James. I'm wearing his t-shirt. But you might not recognize anyone else. If we look at the minutes per game played by these players, they're pretty low in general, except for LeBron James, which indicates that these are role players, which is very surprising because you wouldn't expect role players that an NBA game is 48 minutes. So these players are really, most of them are playing a small fraction of the games. So it's surprising that their impact should be so spectacular. So what is going on? Well, what's going on is that there could be random fluctuations because maybe they didn't miss a lot of games, or they played very few games, and that is basically that introduces a lot of noise in this statistic that we're computing. In order to avoid that, we apply a hypothesis test. Okay, so our null hypothesis is that the player has no impact. The distribution of games with and without the player is exactly the same. It's kind of tricky to start thinking about a parametric model for the test statistic under the null hypothesis. We could do it, but we're going to be lazy. What can we do? We can just apply a permutation test. So let's remind ourselves very quickly, how do we apply a permutation test? We put the point differentials in a long vector where the first n1 games are the games with the player and the remaining n2 games are the games without the player. We compute the test statistic, which is the mean of the games with the player minus the mean point differential without the player. And then we generate k permutations of this vector, where we're like switching the entries. We have to do k permutations because we cannot check all permutations. That would be computationally infeasible. And then for each permutation, we compute the difference between the mean point differential in the first n1 games, remember that they have been switched around, and between the remaining n2 games. And now the p-value is going to be the number of test statistics from the permutations that are above the actual test statistic that was observed, and we have to divide by the number of permutations. So this is the fraction of permutations for which the test statistic is above the one that was observed. That's the p-value of the permutation test. Great. So we do that and we see very small p-values. Great. Are we done here? Like these p-values are all below 0.05. So I think all of them. Yeah, actually all of them. So are we done? Well, no, we're not done. Okay, we just saw that. Here what we're doing is multiple testing, right? There's many. I should have shown you that. Are you convinced? No, you should not be convinced, because there's 1,397 player team pairs, because I'm doing this separately. When, for example, LeBron James went to Miami, we have LeBron James in Cleveland and then LeBron James in Miami, okay, separately. So we have 1,397 hypotheses that we're testing. So it's, very likely that by chance some of them are going to have a small p-value, and it's going to be those that have large test statistics. So what can we do about this? Well, we can apply Bonferroni's correction. So here we have this k equal to 1,397. If we set the significance level at 5%, then Bonferroni's threshold is 3.58 times 10 to the minus 5. We go back to our list of the players that have the highest test statistics, and we realize that only 2 of them are statistically significant under Bonferroni's threshold. Okay, you will be very surprised to see Bruno Caboclo here if you follow basketball. I am going to talk about this specific case at the end of the video. So have some patience, we'll talk about that later. Okay? But for now, basically, we see that this correctly identifies LeBron James as being statistically significant and the rest of the players as not being statistically significant. Now we're going to sort by p-values, and here we're going to see the power of the p-values. If we sort by p-values, then suddenly the list makes much more sense. We have LeBron James, we have Carmelo Anthony, we have Ricky Rubio. Happy to see another Spanish player here. We have Joel Embiid. The list starts making a lot of sense. You can see that their minutes per game are very high. We were going to talk about Bruno Caboclo later, as I promised. Okay, so just bear with me. But so that's a good, that's the good news. Okay, without p-values, we got garbage essentially. Like if we just looked at the highest test statistics, if we use the p-values to order the players, then suddenly the list makes a lot more sense. We identify players that definitely have a strong impact in their games, and in fact, LeBron James is the one that has the most impact when he was in Cleveland, and he played with players that had, that were probably worse than the ones he played with in Miami. So that makes a lot of sense. This also weights how much evidence we have, because LeBron James in Miami doesn't appear because he just missed 6 games. So we cannot get a very small p-value from that, okay? So the p-value is immediately encoding how much evidence we have in favor of the impact of a player. That's the good news, okay? Let's take a look at why this works. As we had seen before in the clutch, we have a lot of players. So here, when in the clutch example, I think probably the null hypothesis held for every player. I really don't think that a player shoots better in the clutch. I mean, defenses are much better in the clutch. It's just kind of a ridiculous thing to say. Here, however, obviously there are some players that have impact. If we can, roughly speaking, divide the players between those that do not have impact, for those the null hypothesis holds, and we're going to see p-values that are distributed essentially uniformly. And we're going to also have some players that do have an impact, okay? And for those, we're going to see p-values that do something like that, okay? Where does this red line come from? Well, from this proof that we had for, when we were talking about statistical significance, that if the null hypothesis holds, then the distribution of the p-value is going to be uniform. So that's great, because then the probability that we end up there is small, but the problem is that now we have a lot of players, right? So the probability, maybe I should have drawn that in red, the probability that one of these null hypothesis players ends up here is relatively high, right? Because look at all the, look at this uniform distribution. So here we're going to have a mixture of players that correspond to the alternative hypothesis, they have real impact, and the null hypothesis players that kind of randomly end up there. This here I'm showing you the p-value below 0.01. Bonferroni's correction zooms into there. Oh, I went the other way. Zooms into there. So now we're seeing p-values from, we're zooming into 0 to 0.001, and Bonferroni's corrections say like, okay, like if we go close enough to 0, then eventually these uniformly distributed p-values are going to become sparser and sparser because we're just zooming in close to 0 until it's very unlikely that one of them ends up there by chance. Okay, that's what Bonferroni's correction achieves. So these players, some of them are probably still kind of noise, okay? And in fact, there could be a player that, you know, if we're unlucky, 5% of the time, there's going to be a null hypothesis player that is going to sneak in there. But this allows us to identify the alternative hypothesis players, which are going to be here. However, as I said, the alternative hypothesis players are not only going to be there, right? You would expect the distribution of the alternative hypothesis players to be something like this. So some of these guys might also be alternative hypothesis players that we're missing because we're very strict. We're applying this Bonferroni threshold to be very strict to avoid false positives. And in fact, this happens because we see Kevin Durant here that barely misses the cut. And Kevin Durant is one of the top players in the history of the game. So obviously he has a huge impact. But, you know, because of the number of games he missed or whatever, this is not statistically significant when we apply Bonferroni's threshold. If we go further down the list, we see other players that are clear false negatives. I hope did I say false positive a moment ago? I meant false negative, right? We don't reject the null hypothesis for Kevin Durant. We definitely should because he has impact and he's barely above the Bonferroni's threshold. We can see here some other clear false positives, including Marc Gasol, another Spanish player. Happy to see him there. Kawhi Leonard, Klay Thompson, Stephen Curry. Obviously, these players had a lot of impact, but we're being extremely strict to avoid false positives because we have more than 1,000 players, more than 1,000 hypotheses that we're testing at the same time. Because of being so strict, we're missing these guys. We're incurring in these false negatives. So there is a trade-off. Bonferroni's correction reduces false positives. It still protects us from false positives, but at the price of increasing false negatives. So if you're in situations when you are actually carrying out many hypothesis tests at the same time, then it's probably a good idea to just accept that you're going to have some fraction of false positives and order your data by the p-value and apply a more lenient rule than Bonferroni's correction. Okay, so what have we learned? We have learned the challenges arising from multiple testing. We have learned about Bonferroni's correction that still protects us from false positives in the multiple testing framework. We have learned that there is an important trade-off between false positives and false negatives. If we have many tests and we apply Bonferroni's correction, at some point we're just going to have a lot of false negatives. And that's it. But I promised you that I would talk about Bruno Caboclo. Okay, so Bruno Caboclo has a p-value that is below 10 to the minus 7. The only p-value that is smaller is LeBron James. So what is going on here? If we look at the data, and it's always good to look at the data when you don't understand something, he actually only played 24 games over 4 years. He missed 200 games. And in those games, the mean point difference was much higher than in the rest of the games. So, do you think that the Raptors were winning because Caboclo was playing? Think about it for a moment. Well, no, right? Like, it's quite obvious that they were making him play when they were winning by a lot. Caboclo was playing because the Raptors were winning. This shows that hypothesis testing, a result can be statistically significant, and this result is definitely statistically significant. We know that the Toronto Raptors were much more likely to be winning by a lot if Caboclo was playing than if he was not. It's definitely statistically significant, but that does not imply a causal effect. We'll talk more about this in a following video. And now I'm done. Thank you very much.